Good day, everybody. We're trying to show that this integer equation does not have any positive integer solutions. And more set theoretically, we're trying to show that there's not any xy. We're trying to say this, that there's no positive integers that are not a member like this, n cross n. That's the Cartesian product of the positive integers, folks, of the positive integers. So we're saying we want to show there are no xy that have that property, okay? So now, one easy way to see why I've made these instructions this way is to note that 0, 4, 5, 6, 6 is a solution. It's easy to check by inspection. And also 4, 5, 6, 6, 0 is also a solution. So those many would call trivial solutions, and I'm trying to find, so those are solutions, but not interesting, okay? We want to show that there are no positive integer solutions, all right? Now, there's this famous result attributed to this gentleman, Simon Salzedo, and in competition, at math competition level, I've seen this called Simon's favorite factoring trick. Okay, and I think the guy's probably not too proud of it. It's a simple idea, not that I would have noticed it, but he's fried much bigger fish than this. But anyway, this is called Simon's favorite factoring trick, I believe. Okay, now let's take a look at what his idea was. Does something very, very simple here. He just adds 1 to both sides. His technique is more general than this, of course. But if you add 1 to both sides of this equation, you get an equivalent equation. Notice you have to bump up 4566 to 4567. Okay? Now, so we get to this point right here where we can factor out an x plus 1. Now, it's useful to think of this, and this bothers some beginners. Myself still, there's an understood 1 here, and so when you factor this out, you would have x plus 1 times y plus 1, right? Very simple, but the 1 sometimes for beginners, and I hate to keep using the word beginners, I don't mean it pejoratively, but you don't think of the 1 being there, and so a lot of people will leave this 1 out. They don't understand the 1 belongs. All right, now notice that one possibility would be to equate this with the trivial factors, let's call it that, 4, 5, 6, 7. Like that, okay? Now, notice though that this is going to lead to an issue, because no matter which way, if you associate 1 with this factor, that implies x would be equal to 0, right? It's the only one that works, but we're not interested in those solutions, right? And similarly, you would get y equals 0 if you equated the other, right? So you see, that would not lead to anything in terms of, that would not lead to a valid solution as far as looking for solutions in the positive integers, okay? Ordered pair solutions in the positive integers. So we're thinking, okay, great. But one thing that's very, very useful right here is that 4, 5, 6 is prime. Okay, so this is the only factorization of 4, 5, 6, 7. And again, that's kind of a famous prime all by itself, because I don't think there's any other 4-digit or any other consecutive digit primes like this that exceed 4 digits. I don't know if there's any in the 3-digit range or not, actually. But this is definitely an oddity. It's in terms of just appearance alone. Now, so it's prime, and one way to check this, and again, that's, quote, the hardest part of the problem. 4, 5, the square root of 4, 5, 6, 7 is, I think it's less than 68, and you can check that if you want. It's 68 squared is a bigger number than this, so it's less than 68. So that means the only primes we have to check would be the primes 2, 3, and I won't write them all out. 2, 3, 5, 7, and then we'll put dot, 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 67's prime, right? So you would have to check to see if this number is divisible by these primes. I don't know how many primes that is. It's pretty clear it's not divisible by 2, 3, and 5 just by inspection. And there's a divisibility test for 7 and 11 and all that. But you basically, this would be more or less a manual process. You would find out that none of these are divisors, okay, of 45, 67. And that's an elementary proof that that means that 4, 5, 6, 7 is prime. Okay, so again, check these divisors if you don't trust me on 4, 5, 6, 7 being prime. And the proof of that is kind of nice. It's an interesting little proof of why checking just all the prime divisors less than the square root of the number is sufficient. Okay, so anyway, there are no solutions, right? There are no solutions because 4, 5, 6, 7 is prime. This is the only factorization of 4, 5, 6, 7. That's the definition of a prime. And in either case, you end up with 0 as one of the solutions, which is an invalid solution as far as the context of this problem. So we can write down QED at this stage. There are no solutions. And of course, the same kind of result would hold for any prime based on the logic we used right here. Okay, that's it, folks. Thanks for viewing.